So now I'm going to talk about my second pin diodes based study, which is aluminum nitride based pin diodes. Uh, the breakdown field of semiconductors is scales with the band gap of semiconductors, and we know that the critical electric field of aluminum nitride is approximately 3 times that of gallium nitride, resulting in a theoretical improvement in terms of Baliga's figure of merit for aluminum nitride over gallium nitride of approximately 17.5 times. Some exciting applications of aluminum nitride-based devices are operation in extreme environments, high-temperature electronics and sensors, power distribution, and high-power radio frequency electronics. Some other amazing applications of aluminum nitride include deep UV LEDs and lasers, solar blind detection, and acoustic devices. My major motivation for this study is that aluminum nitride ranks in the top 2 materials in terms of ultra-wide bandgap semiconductor performance parameter. For example, the critical electric field of aluminum nitride is 1.5 times that of gallium oxide, 3 times that of gallium nitride, and approximately 5 times as compared to that of silicon carbide. But up to now, the major limitation was p-type doping, the lack of doping in aluminum nitride. And we first proposed beryllium doped aluminum nitride p-type films grown via metal modulated epitaxy. So I performed a study on first time achievement of p-type aluminum nitride films via beryllium doping. The solubility limit of a dopant is determined by the formation energy of the dopant. Formation energy further depends on the atomic radii matching and the bond strength of the host versus dopant atoms. We know that in case of gallium nitride, magnesium closely matches in terms of atomic radius with the radius of gallium in gallium nitride, so it is found to be the best p-type dopant in gallium nitride. By similar hypothesis, beryllium closely matches with the atomic radius of aluminum in aluminum nitride and is potentially the best candidate as a p-type dopant in aluminum nitride. Generally, the theory agrees that the activation energy of beryllium is lower as compared to the activation energy of magnesium in aluminum nitride. The activation energy of beryllium in aluminum nitride is found to be approximately 300 milli-electron volts. In traditionally grown magnesium-doped gallium nitride, we find isolated impurity levels, which is also depicted by its 2 peaks in photoluminescence measurements. Now, on the contrary, in metal modulated epitaxy, we can achieve high solubility, and also we achieve impurity band formation overlapping the valence band of the semiconductor, which is also depicted by a single photoluminescence peak where the band overlaps that of the gallium nitride 3.4 electron volts band gap. So we have achieved an improvement in terms of activation energy for magnesium doped gallium nitride, reducing it from 200 to 50 milli-electron volts as compared to literature. So now we wanted to see if we can improve the activation energy of beryllium in aluminum nitride as well. This led to my study of growing beryllium doped aluminum nitride on top of HVPE aluminum nitride templates with buffer layers. We achieved streaky reflection high energy electron diffraction patterns indicating smooth surface morphology. From AFM comparison of a beryllium doped aluminum nitride versus undoped control sample, we see that beryllium doping improves the surface morphology. Later, I deposited platinum, palladium, gold contacts on these films for Hall measurements. And from extensive optimization of the contacts, here I've shown a comparison of the post-annealed beryllium doped aluminum nitride versus pre-annealed contacts. And the annealing improves contacts conductivity by approximately 6 orders of magnitude. Furthermore, from comparison of a beryllium-doped aluminum nitride versus annealed undoped aluminum nitride film, we see an improvement in approximately 4 orders of magnitude. So it's actually the beryllium doping which improves the conductivity of these samples. Later, I wanted to validate the conductivity type of these samples with both Hall measurements and also hot probe measurements. But first, I calibrated Hall and hot probe measurements for our standard P-type, UID, and N-type gallium nitride samples. Later, I grew beryllium-doped aluminum nitride samples at a substrate temperature of 600 degrees C at different beryllium doping levels. Beryllium doping levels where the Hall results were questionable, beryllium doping levels where we see massive compensation, and beryllium doping levels where we achieve reliable results in the range of 10 to the power of 15 to mid 10 to the power of 17 per centimeter cube, resulting in activation efficiency of approximately 5%. I also grew beryllium-doped aluminum nitride at 700 degrees C growth temperature and achieved even higher Hall concentration of 3 into 10 to the power of 18 per centimeter cube. And the conductivity type was also validated from hot probe measurements. Later, we sent these samples to Lakeshore for conductivity confirmation and also for temperature-dependent Hall measurements to extract the activation energy of these samples. And we found a very low activation energy of 37 milli-electron volts. To summarize the key results, we at Georgia Tech are the first experimental group to report success in achieving P-type aluminum nitride films with a very low activation energy of 37 milli-electron volts. We have achieved as high as 3 into 10 to the power of 18 per centimeter cube Hall concentrations. And we believe that with this achievement, aluminum nitride is no longer just an insulator or substrate. It has graduated to a semiconductor. Next, I wanted to pursue a research journey towards Homo-junction aluminum nitride, and in this regard, we introduced silicon material into one of the effusion cells in our MBE chamber. Silicon, we know that is a shallow donor in gallium nitride with activation energy of 17 milli-electron volts. However, with increase in aluminum content in aluminum gallium nitride, its activation energy increases to above 200 milli-electron volts. So although the atomic radius of silicon closely matches with aluminum in aluminum nitride, but due to several reasons, for example, formation of aluminum vacancies, DX formation, which is transition of silicon from shallow to deeper states, and threading dislocations, the activation energy of silicon in aluminum nitride is high. So I utilized the high crystalline conditions of MME and I grew silicon doped aluminum nitride films in the doping range of 5 10 to the power of 17 to 7 10 to the power of 19 per centimeter cube. And I achieved a high electron concentration of 6 into 10 to the power of 18 per centimeter cube, which is 6,000 times higher as compared to the previous best electron concentrations in silicon doped aluminum nitride. So now the stage was set to perform the final study, which is first time Homo-junction aluminum nitride diodes. This slide shows the layer structure diagram of these diodes, where I grew the N-type aluminum nitride and the I-type aluminum nitride, which are silicon doped at 800 degrees C substrate temperature, and I grew the P-type beryllium doped aluminum nitride at a substrate temperature of 700 degrees C. From PTLM comparison of a planar P-type film versus the PTLM on the device, we see that our current conductivity was slightly lower as compared to the planar film, but they were still comparable. However, For the N-type aluminum nitride device contact, our current conductivity was 2 to 3 orders of magnitude lower as compared to the planar film. We suspect that this is due to the damage introduced during the etching process. I repeated this study, but once again I encountered the same issue, and this is something which requires improvement in the future. In this slide, I've shown the JV characteristics, both forward and reverse bias, for these homojunction aluminum nitride diodes. I achieved approximately 7 orders of magnitude rectification for these diodes, and we achieved a nearly ideal turn-on voltage of approximately 6 volts for a 6.1 electron volts semiconductor. However, we see a high series resistance evident from the long tail of the semilog plot, which is attributed to the high N-type contact resistance, and with improvement in the contacts, we can achieve even higher performance for these devices.